All right, so very happy to see you guys again. Now I'm going to show a little bit of our research progress on catalysis, because my group start to work on data-driven design of catalysis for quite a while. Actually, in the past 2 years, this is my ACS Spring talk on data-driven discovery of active single atom sites from carbon-supported single atom catalysis to high entropy alloys. Okay, so this is my research group by then. Okay, so actually one of our postdocs just left. So currently we have 2 postdocs and 3 PhD students, and also hopefully we're gonna have new members join these 4. Okay, so today we're gonna start with actually carbon-supported single atom catalysis, which is just classic single atom catalysis. People have studied that for quite a while. And then we're gonna go to intermetallic based single atom catalysis, and also high entropy alloy based single atom catalysis, high entropy alloy based catalysis. Okay, so it's actually a path of looking for more diverse local structures, and we gradually realize, maybe high entropy is kind of a more interesting compared with classic carbon-supported materials. Okay, so let's start with the first research. It's actually a paper published the end of last year and early this year. So we want to study, graphene-based single atom catalysis, which is a very classic system. There are kind of an infinite amount of works so far. Okay, so the central atom we can choose will pretty much be typical 3D and 4D and 5D elements. Well, on the other hand, the local environment we can choose will consist of, depends on how many carbon you have. And in a lot of situations, people dope other species like nitrogen is very typical dopants that are introduced into, the graphene monolayer. Okay, so in this work, we actually did a high super screening of all 5 types of local structures, and also about 28 transition metals. We do not have TC and Hg because one is radioactive, the other one is a liquid. I don't think people are going to use them in catalysis anyway. And by this is gonna end up with a throughput of like 560 60 calculations of different substrate and different absorption models. And then we plot everything we have into a heat map, which is kind of interesting because we do see some of them are experimentally reported as good electrocatalysis. Okay, so like vanadium, chromium, iron, cobalt, nickel, and moly based are all predicted. Okay, so we actually list all these references in our paper. Feel free to read our paper if you're interested. And then we also realize there are a bunch of new candidates which can be as good as those reported candidates, which is kind of, highlighted with the black square. Okay, so and on the other hand, the first one is actually for HER. For the ORR, we do also see that we have seen a lot of promising candidates from prediction, where we have also something interesting from our simulation. Okay, so and we want to look for if there's any trend for it. There has been paper published saying that there are perfect trends for single atom catalysis. So we are trying to see if we can see something as perfect as those literatures. I mean, this is just this is actually not very high throughput ones, because in this work is only study 5 metals, right? So we have way more metals, and we want to see, like, I mean, for instance, the famous D-band center does have a correlation with overpotential or like absorption energy of anything or not. So we apply our data. We have like 500 DFT calculations, right? So ideally we want to see something like this, but eventually this is what we see. Okay, so we can barely see some kind of a trend, but it's not really very obvious trend, right? So, and you cannot really fit some curves into this trend. I mean, these black lines are just to guide your eyes. Okay, so we have some kind of a correlation. Depends on the amount of valence electrons. Okay, so instead of quantifying that, I realized maybe the only thing we can do is actually to briefly explain what is going on using, molecular orbital theory. Okay, so it's pretty much depends on two things, right? So the metal center and local environment. And we sort of end up with the conclusion that, the metal center actually will pretty much dictate the rough position of the absorption energy because of the periodicity of d orbitals. Okay, so if you do not have the right valence electrons, the absorption energy will typically be too big or too small. Otherwise, absorption energy is more tunable. And the way we tune it actually from the local environment. Okay, so and this is pretty much depends on the local hybridization between the carbon and the metal. Okay, so to study that, and we kind of first of all plot the d band center. It's actually d orbital center because we do not have a periodic arrangement of the metals, and we do see that we see a very clear periodic trend, regardless of what exactly the metal is. It's pretty much depends on the valence electrons you have. Okay, so at the same time, we can kind of divide them, depends on whether they are early transition metal, they are kind of late transition metal, or they are transition metals in the middle. Okay, so we kind of divide them into group 1, 2, and 3, and later we're going to discuss a little bit more about it. Because once you divide all the metals in this way, you will see pretty much 3 types of trends going on. Okay, so this can actually be explained by molecular orbital theory. Okay, so this is actually the molecular orbital diagram when you have hybridizations in a graphite or graphene monolayer. Okay, so what's going to happen is like the transition metal going to hybridize with the p orbitals and s orbitals in carbon. And you're going to form some bonding states, which denoted as A1G, B1G, and EU, and followed by B2G and EG, and then you have non-bonding state, and followed by anti-bonding state, right? So in that case, the filling of the electrons in those diagrams going to dictate actually, the absorption energy. Okay, so we have 3 groups, right? So group 1 is like when you have 3 electrons and 4 electrons in the outside shell. What's going to happen is like the adsorbate. It could be hydrogen, could be hydroxide. If it's a hydrogen, because the energy is so different from carbon and nitrogen and transition metal, right? So what's going to happen is like the hydrogen, which is a silver atom, going to directly goes to the empty bond. And by definition, if you only have 3 and 4 electrons, you're definitely going to have empty bond in the bonding state, which is green. Okay, in that case, the energy add into the system will pretty much become the energy state of that bonding state, which is well defined, right? So similarly, when you have hydroxide, it's gonna start to hybridize with these bonding states, and again, it's kind of dictated by the exact location of the bonding state. On the other hand, and as a result, if you look at the absorption energies, I mean, for both cases, they will be very different because it's pretty much related with the exact local structure and how hybridization goes on, right? So because hybridization controls the energies of the bonding state. On the other hand, if I have V5 to V9, something different will happen. Okay, so hydrogen again has very different energy compared with the rest of the atoms in the system. So you're gonna directly go to the lowest unfilled state, right? So in this case, it's actually the blue state. The blue state is actually a non-bonding state. Okay, so B2G and EG, as you can see from the diagram, is pretty much coming from the transition metal. It's not actually coming from the carbon. Okay, so those states is pretty much dictated by the metal itself rather than the hybridization. And while on the other hand, and because of that, if you calculate the hydrogen absorption energy, it's actually irrelevant with the local coordination environment. Different colors here tells you different local coordination environments. You can have 4 carbon, 3 carbon, 1 carbon, and the rest of them will be nitrogen. Okay, so but on the other hand, if you have a hydroxide, it still prefers to hybridize with the bonding state. So as a result, the energy difference will still be very different across different local environment. And if it goes to the late transition metals, again, hydrogen gonna go to anti-bonding state, and hydroxide gonna have to hybridize with bonding state again, because they're gonna rehybridize it. The hydroxide will rehybridize with graphite or transition metal anyway. Okay, so in that case, in both cases, the absorption energy is pretty much depends on the local hybridization, so it's very system dependent. Okay, so this is kind of some kind of a qualitative trend that we can observe for single atom catalysis, but honestly, we cannot go a bit further than that. There's no way for us to really quantify, the absorption energy with a clear and accurate enough model. And this does not necessarily mean that there's no way of quantify that. So to kind of facilitate the exchange of information, we actually open source all the data, all the DFT raw data in GitHub. Okay, so if you're interested and if you want to do anything on this 560 DFT calculated absorption energies, feel free to get access to our data, and please cite our paper if our data is useful to you. Okay, so we also have this kind of interactive heat map to directly give you a sense of the performance of those carbon-supported single-atom catalysis systems. All right, so that's kind of a short conclusion, right? So we sort of realize, local environment can do something, but what it can do is pretty much limited by the transition metal species. You unfortunately have to deal with some special transition metals. Okay, so we have very limited space. Then I'm thinking like maybe we should go to intermetallic. Okay, intermetallic, actually we have a lot of intermetallics in the databases, both, in like a computational database like Materials Project, or like an experimental databases like, ICSD, and open crystallography databases, etc. Right, so that gives us more tunable space. So ideally, these are some examples just to show you that intermetallic can be really different from each other. Okay, so we did a high super screening of all intermetallics starting from 31 transition metals. We also include some of the real earths like lanthanum and selenium. That's why it's end up with 31. And also, we searched through Materials Project, and we found about 2,300 intermetallic with 2 metals and 3 metals, and we only choose those with energy Balho less than 50 MeV per atom because we want to make sure people can make those compound experiments, and it's eventually end up about 462 intermetallics. And then we kind of brute force enumerate all these, low index surfaces with Miller index, any one of them smaller or equal to 2. And also we kind of limited our calculation a little bit because once you create a supercell and a slab model, the size of the slab can be really large. So we only choose those that has less than 200 atoms per slab. And eventually you're gonna end up with like it's quite a lot. It's like 11,000 of surface structures, and we actually compute this 11,000 of surface structures in the gas electronic structures. So this is pretty much about the distribution of the compound. So the color tells you how many surfaces we eventually end up with in our DFT calculations. And in addition to that, we start to use and develop some descriptors to describe those, density of state, and hopefully we want to look for some good catalysis for either HER or ORR. And we want to bring out some of the useful descriptors that people use, right? So people use something like D-band center, D-band width, and the skewness of D-band. the cortices of d band. This is pretty much like the nth moment of density of state. Okay, so which essentially you can take an integral of the power of the energy state multiplied by the density of state, which is a low e here, right? And you take an integral. The n here tells you this is nth model of density of state. So we actually implement that in addition to some kind of a shape factors. Okay, so this is kind of an upper shape, which intuitively this is essentially the location of the anti-bound state according to the paper report put it in the references. So eventually we have 5 descriptors about the shape of density of state. Okay, so and we kind of plot that with respect to all the metal species that we considered. And we do see there is kind of a pattern going on here, but if you can see that some of the violins is actually quite broad, that also means that intermetallic offers a very broad tunable space for some of these properties and for some of these metals. Okay, so and then we want to kind of zoom in to see if we really see some good material candidates. Okay, so we actually found these 2 candidates which is already reported in experiment, and we computationally verify that, and they do show very promising properties as HER catalysis and ORR catalysis. In addition to that, all those results is actually open source again. This paper is actually published because I'm recording this actually a few months later after my ACS talk. So this paper is actually already published in Journal of Material Chemistry A. Okay, so please feel free to check my paper, and we actually provide the link to our database, and you should be able to access all these 11,000 of DFT computed surfaces, and we actually screened more than 100,000 of single atom sites. Okay, so I hope those electronic structure information can provide some useful guidance of how to design intermetallic based catalysis. But this is not yet the end of our story. We realize still we have some kind of a periodicity. It's pretty much governed by the metal species, and we do not actually have too much structures for intermetallics. Eventually, we thought we have a lot, but we end up with only 400 structures for 30 metals. It's actually not that many. Okay, so then we realized maybe we should be more complicated. Why don't we just go to high entropy alloys, right? So in high entropy alloys, you can put as much as metals into it, and you're gonna have a very diverse local environment, right? So because everything is random. In this case, we did a high throughput screening first of all the possible high entropy metal alloys. Again, we screened through 28 metals, and we actually have 378 of binaries and 3,200 ternaries and 20,000 quaternaries and 98,000 quinaries. We actually calculated all of them. Okay, so and up to quaternaries, and for quinaries, we have some sampling strategies to calculate only in those synthetically accessible ones. Okay, so and this is actually a work done by my first PhD student. We eventually end up with 72,387 DFT computed compositions covering the typical 3 types of crystal structures. Okay, so this is kind of a distribution of the ground state in terms of each phases, and actually some of the phases after DFT relaxation will not be one of these 3 phases targeted. They're going to relax into something else, or they're going to become amorphous eventually. Okay, so this is a work actually recently got published in Advanced Materials, and in this work we actually develop a machine learning based phenomenological theory that helps us not only by just looking at the statistic and then get some trend from statistics, we also want to be able to predict directly, which phase you're actually going to form when you mix different metals with different phases. So we come up with a descriptor called tau, and to compare that with the most widely used descriptor, which is valence electron concentrations. and our descriptor actually performs much better, because by just looking at this graph, you see that the valence electron concentration will totally mispredict all the HCP based high entropy alloys. But in our model, the HCP can be well captured and kind of aligned in the middle of these two classes of high entropy alloys. Okay, eventually I just want to show that we are also developing machine learning models, and this is actually a very old model. Now we are much better. Okay, so we can actually approximate infinitely close to the DFT arrows. DFT arrow is pretty much like a few MeV per atom. So currently our machine learning model can actually go to that kind of accuracy, which sounds really exciting and promising. So we're gonna update a little bit more in the future once our research get published, and I'm very happy to share with you guys the recent progress on this direction. And at the very end, I would like to thank my students again. This is my team at March of this year. But actually, most of the research is actually done by my first postdoc Zhenda and my first PhD student Lin Wan. Okay, so and Zhenda He actually did the paper on the single atom catalysis and intermetallic based catalysis. Well, Lin actually did the work on the high entropy alloys. Okay, so that's pretty much for my presentation this time. Okay, so I will see you in my next video.